Alright, so we're going to look at turning functions today and figure out how to get our robot to turn 90 degrees. So if we looked at our robot, we have a wheel on this side and a wheel on this side. And we have an important measurement that we need to find from the center of this wheel to the center of this wheel. And that distance from here to here is called the wheelbase. And this is important for doing both swing turns and point turns. A swing turn, we would keep one motor at 0, so it would be stationary, while we turn the other one around it. So it would be a swing turn, it would swing on this wheel here, and it would follow kind of this path as it would go around. And we're going to go to 90, so we're going to go from here to here. So our wheel then would be in this orientation here, and then this one would be turned, I guess it would be kind of like this. This would be back a little bit. As it swings and pivots right on the center point of that. This would be 90 degrees, and this wheelbase, if this is our robot motion, this is now a circumference that the robot is making, and the wheelbase is now a radius of that circumference. So the circumference of the robot is equal to 2 pi times the wheelbase. Okay, and this is also equal to 360 degrees, and if this is the length that the wheel has to turn, that circumference, we can then calculate the amount of ticks, because we know that the circumference of the wheel is equal to 1 rotation, and we also know that 1 rotation is equal to 360 ticks if we're using the external encoders. Okay, and the circumference of the wheel is going to be pi times diameter of the wheel, so that's going to be equal to 360 ticks. We can come up with an equation using these conversion factors. So if I'm looking for the number of ticks that are equal to 90 degrees, I can convert degrees to inches using this conversion factor. So for every 360 degrees, I need 2 pi times wheelbase inches. And now I'm in inches, and I can convert inches to ticks, because for every 360 ticks, that is this many inches. Pi times diameter of the wheel. Inches. And if you look at your units, they cancel. Inches with inches, degrees with degrees, and now you're left in ticks. So if I were to write this equation out in robot C, ticks would equal, I'm going to use this as a variable now, because it doesn't have to be 90. I'm going to use a variable called degrees, times, and then if you look, we can do some canceling here. So it's kind of nice using the external encoders, because the 360 here cancels with that. Pi cancels with this. So basically it's 2 times the wheelbase and then divided by the wheel diameter. So that's the equation that we're going to use now to solve for ticks, where before we solve for ticks in terms of inches using the number of ticks per rotation and the wheel circumference, we're using a little different equation now to find the ticks. And this is the ticks that the left motor would need to get to in order to make a certain degree turn holding the right motor stationary. So we'd set up a while loop with a turn function using that. Let's look at the other type of turn. So this is one equation that you could use. Again, this is for a swing turn. We'd use this value. And we could do a swing turn right and a swing turn left. So if I were doing, so I'd set up a couple of functions where it would be swing turn right, and then I'd pass it maybe a float in degrees. And then that way I could call swing turn right and pass it a 90, and now it should make a right turn like that. The other one would be a point turn. So again, here's our robot, the wheels. This time we're going to be spinning in place. So we're going to be spinning about this point right here. So this wheel is going to go this way, and this wheel is going to go this way. So now what is my circumference? Well, here's my wheelbase. Still the same wheelbase, but now the wheelbase is the diameter of that circumference. So we have a little bit different relationship. The circumference of the wheel now is pi times the wheelbase. And if you look at our last equation, if you wrote that down, you'll notice that circumference, oh, I'm sorry, not circumference of the wheel. It should be circumference of the robot. Sorry about that. Last time the circumference of the robot was 2 pi wheelbase. This time it's just pi wheelbase. So how do these two relate? Well, this circumference is now 1/2 the circumference of the larger when it's a swing turn. So the difference between the equation we're going to write for this ticks and the other ticks is just we're going to divide this ticks by 2. So we can take those ticks, that same equation, so I can copy this exact same thing, but now if we divide it by 2, what's missing? This right here. So it's going to be degrees times wheelbase divided by wheel diameter. Now this is only true for what type of encoders? Yeah, the red ones, the external quadrature encoders. That's the only time this equation is true. If you're using integrated encoders, you have to go back here and change this value right here, which will not be 360. It'll be 240.448, and that's not going to cancel with this. Okay, so you're going to have to leave those two numbers in your equation when you do it. And if you wanted to, you could reduce this down to 1/180. That's fine. When you do that, you could reduce those numbers, but this number still needs to be the number of ticks per rotation for your particular motors. So just be aware of that. This equation only works for the external encoders when you're doing this. Now we have to think about, okay, when we turn, what do we want this motor or this encoder to get to? This one we want to go to a positive ticks value, and this one over here is going to get to a negative ticks value. So we need to say while this motor is less than ticks and while this motor is greater than negative ticks. Everybody get that? So while the left encoder is less than ticks and the right encoder is greater than negative ticks. So this will start off at 0. So is 0 greater than negative 50? Yes. Is 0 less than 50? Yes. Let's say it moves down to here. So this would go to negative 25. This value would go to positive 25. So is 25 less than 50? Yes. Is negative 25 greater than negative 50? Yes. So it's going to still keep turning until we get to that point. So let's make a point here. Let's say we got to an encoder count of 60 and an encoder count of negative 52. So is the left encoder 60 less than ticks? No. And so right there it's false, it kicks out because it's an and. Is the right encoder greater than negative ticks? Well, negative 52 is not greater than negative 50. So no, that's false too. So it would kick out of your while loop and then you would stop. I'm going to encourage you that once you do your turn functions, that you want to then check your encoder values once more. So let's say we turn the robot and we get it to here, and it's not stopping right at 90 like we want. We've p-looped it, we've slowed it down so it gets to there, but it's maybe still drifting a little bit by. What you might want to do is recheck the encoder values and then recorrect it. So let's say, for example, this is my robot, okay, and I'm right here. I turn, and I go, and then I start slowing, and I slow, and I just barely drift by the 90. Well, I can check my encoder values once more, and then I can back it up really slowly until it hits exactly 90. So that's something you could do, and I encourage it because, again, turns are going to make much more of an impact on your robot than if you just drift by a half an inch or so. If you miss your turn by a half an inch, over a 5-foot distance, you're going to be off quite a bit from your intended target. So again, check those values on the encoders before you actually move on in your code. Put that right in your function for your turn left or your turn right. Again, you can do a swing turn, you can do a point turn. Either one is appropriate. Thanks. Have a great day.